Hello to all viewers. Thank you for watching this video. My name is Halimi Najibi. I'm a PhD candidate at the Embedded Systems Laboratory in EPFL, Switzerland. I'll be presenting my work on collaboration with the Nanyang Technology University in Singapore, which is entitled Towards Deeply Scaled 3D MPSoCs with Integrated Flow Cell Array Technology. During the following 20 minutes or so, I will begin by presenting the motivation behind our research work, and I will also introduce the novel flow cell array technology developed in our lab for thermal and power management of 3D MPSoCs and the importance of investigating their sustainability with deeply scaled technologies. Then I will present the overview of the 3D MPSoC setup used throughout this work to analyze the scaling of FCA power and thermal capabilities. Next, I will explain our methodology for estimating the evolution of the power consumption of 3D MPSoC dies when fabricated with more advanced CMOS technology nodes. I will also show you our power consumption analysis of deeply scaled 3D MPSoCs and our thermal and voltage analysis results. And finally, I will conclude with a summary. So let's start with the introduction. Nowadays, as a large number of modern applications, such as machine learning, for example, requires high computing power as well as heavy data exchanges. They typically run in multiprocessor systems on chip that contains various processing elements such as multiple CPUs or GPUs and accelerators, and sometimes different types of memories. The continuous demand for more performance MPSoCs has driven the CMOS industry to scale down the transistor by reducing the technology feature sizes. And additionally, as the devices shrink, modern structures such as the FinFET are used to enable the required high performance. However, the transistor scaling also causes high device leakage and temperature, not to mention the limited scaling of the interconnect, which remains a major limitation of system performance. In this regard, 3D integration with through silicon via technology, or TSVs, enables vertical communication channels and generally a high bandwidth for data transfers. But 3D stacking also means increasing the power density of chips and therefore the temperature and the temperature-dependent leakage, and also a more challenging power delivery. In this context, the flow cell array technology, or FCAs, was developed as a solution to the thermal and power challenges of 3D MPSoCs. The FCAs are microchannels that are etched in the silicon substrate of the stacked die. These channels are filled with an electrolytic liquid that serves two main functions. First, it absorbs the heat and serves therefore as on-chip liquid cooling. And second, the electrolytes chemically react as the temperature increases, and they generate an additional power that can be used in the 3D MPSoCs. The FCAs have been prototyped, and an electrothermal model has been developed to enable simulating their performance in different 3D MPSoC architectures. In previous works, we simulated the on-chip liquid cooling capabilities using a compact thermal simulator called 3DICE. And we showed that FCAs are able to reduce the temperature of a high-performance system by up to 45 degrees compared to traditional fan-based cooling. We also proposed to integrate them as additional power sources in the power delivery network of the 3D MPSoC. And we have done that by directly connecting the FCA electrodes to the back end of line. And to perform SPICE simulations and analyze their performance, we developed a compact model of the flow cells according to the relationship between temperature, voltage, and current of FCAs. We showed that the FCAs can reduce the voltage drop in the 3D power grid by up to 20%, and therefore limiting the performance degradation. Now, as we move towards newer technologies, the 3D MPSoC thermal and power challenges aggravate. The device geometries are getting smaller and smaller, which results in higher transistor density in the dies, and hence more switching activity and higher dynamic power, which leads to higher temperature and therefore higher chip leakage. However, as the CMOS technology shrinks, the transistor operation voltages are lower, and luckily they approach the operation voltage of the Fcas that leads to the optimal on-chip power generation, which is around 0.6 volts. That being said, this work aims to determine if the Fca technology continues to be this efficient power and thermal management solution for 3D MPSoCs when they are fabricated with deeply scaled technologies. Hence, we propose a methodology for modeling the evolution of the dynamic and leakage power consumption of 3D MPSoCs when fabricated with different deeply scaled CMOS technologies at constant area and constant frequency. We then evaluate the scalability of Fca on-chip liquid cooling capabilities, and we demonstrate their effectiveness compared to other state-of-the-art high-performance cooling strategies. Furthermore, we show that the voltage drop reduction capabilities of Fcas also remains significant at the technology scales due to better leakage reduction and higher on-chip power generation. And finally, we motivate the design of deeply scaled 3D MPSoCs using Fcas for power and thermal management by saving additional power grid requirements such as TSVs and metallization layers. Throughout this work, we will use as a baseline setup a two-layer 3D MPSoC to model the power consumption evolution with technology and analyze the sustainability of Fcas. This 3D MPSoC is constituted of one multi-core processor and on top of it, 4 second-generation high bandwidth memories, each having 4 stacked DRAM layers. The Fcas are placed in both the memories and the processor, and the TSVs are placed for power delivery and for interlayer data transfers. Based on this 3D MPSoC setup, we will explore 2 different power consumption profiles for the processing layer. The first power consumption profile is based on the IBM Power 8 general purpose multi-core processor. The original Power 8 is synthesized with the 22 nanometer silicon insulator CMOS and has a size of 22 millimeters by 29. The original Power 8 has a total power consumption of approximately 190 watts, and we model its consumption profile using a real measured power map that shows very important gradients of power density between different regions, including multiple high-density spots. The second power profile is that of the Google Tensor Processing Unit, or TPU, which is a machine learning accelerator architecture. We based our analysis on the second version of the TPU, which is fabricated using the 28 nanometer bulk CMOS and has a size of 20 millimeters by 15. The TPU V2 has a total power consumption of 75 watts, and to model its power distribution between the different elements, we use an area, power, and timing modeling framework, which allowed to estimate the power map. The TPU has generally lower density hotspots and has a more uniformity for each of these components. Now that I presented the 3D MPSoC architecture we have based our work on, I will now explain our methodology for scaling the power consumption of the processing dies if they are fabricated with more advanced technologies. To keep the same 3D MPSoC setup, we assume that the processing die keeps the same original size, which means that as the technology shrinks, the number and size of cores are scaled accordingly. Also, to compare the chips with the same performance, we assume the same operation frequency. Now, the first part of the total power consumption is the dynamic one, which we want to scale for a fixed cell size. The dynamic power per cell is calculated for each technology node using the total power per transistor times the number of transistors, which is relative to the transistor density. The transistor density is scaled based on different technology parameters, namely the contacted gate pitch and the minimum metal pitch. And the dynamic power per transistor is estimated for each technology node based on the device switching energy of a ring oscillator circuit model. Based on all these parameters, the dynamic power consumption of the original dies are estimated for more advanced technology processes. All the parameter values we have used in our analysis are based on reported data from the manufacturing industries, as well as the international roadmap that shows predictive scaling ground rules. And all these references are available in the published paper. Now, the second and more critical part of the total power consumption of the dies is the leakage, of which we want to analyze the evolution as transistor size scaled down. The cell leakage is calculated using the number of transistors and the leakage per transistor. The first element is calculated the same way as for the dynamic power consumption. As for the leakage per transistor, typically the technologies are designed to maintain the same leakage per gate width at the reference temperature, which is typically 25 degrees. And for high performance systems, the transistors are typically designed to leak about 20 nanometers per micron. And besides, the leakage of the devices also depends on temperature. In fact, it grows exponentially with temperature regardless of the process. For our analysis, we extracted the temperature dependency of the leakage of transistors by modeling and simulating various standard gates using multiple sub-20 nanometer technologies. And we observed that 50 degrees of heat can cause up to 10 times higher leakage. Therefore, an effective cooling of 3D MPSoCs become essential to limit the overall power consumption with deeply scaled process nodes. Talking about 3D MPSoC cooling strategies, we will compare the efficiency of FCA on-chip cooling with two state-of-the-art methods. The first one is the traditional and widely used fan-based cooling. As an example of the fan-cooled Power8 processor, it reaches a peak temperature of 90 degrees when in full usage. The same fan-based solution is scaled to achieve the same peak temperature by increasing the fan speed, size, and other parameters. The second cooling strategy we used for our analysis is the Aurora Supercomputer Advanced Liquid Cooling System, which is used for a high-performance multi-processor platform that includes multiple Intel processor and multiple NVIDIA GPUs. This cooling strategy achieves a peak temperature of 95 degrees for the Intel processor, for example. It is also scaled to maintain the original efficiency, which involves changing different parameters such as the cold plate dimensions or the materials. Using these different cooling systems, we evaluated the power consumption of the processing layer, namely the Power8 MTPU, when fabricated using smaller technologies from 14 to 3 nanometer FinFET CMOS process. As I mentioned earlier, we kept the same die size, assuming bigger and more cores, and we also assumed the constant operation frequency. I show here the dynamic power and the leakage of both the Power8 processor at the reference temperature with both the Aurora and the FCA cooling. We observed that the dynamic power does not have a monotonic evolution because it depends on parameters with opposite scaling trends. The leakage at the reference temperature of 25 degrees increases as technology scales due to higher transistor densities. The leakage using FCA cooling increases as well due to higher temperature and higher power densities. And finally, the leakage using the Aurora cooling achieves even higher values due to the exponential growth of leakage with temperature. Similar observations also apply to the TPU power consumption. And hence, we can say that the leakage is becoming the major power consumption part for ultra-scaled dies and therefore an efficient 3D MPSoC cooling is necessary to limit it. And in this context, we will compare the cooling capabilities of the Fcas and the two other cooling systems using the 3D ice compact thermal simulator. We extract the peak temperature of the Power 8 based and the TPU based processing dies for the different process nodes. And we observe that the Fcas are able to maintain the peak temperature of the dies under 53 degrees, and that is achieved without changing any Fca design parameters, such as the dimension or liquid flow rate, even though the power density almost doubles between the original die and the ultra-scaled one. As for the fan-based cooling designed for meeting the Power 8 temperature constraints, the Fca achieves between 41 and 71 less degrees. And the Fca also outperforms the scaled Aurora cooling system by up to 32 degrees. And this shows that at their current advancement state, the Fcas are still a first choice 3D MPSoC cooling strategy. Now let's move to the power performance of Fcas, and particularly their ability to reduce the overall voltage drop in the dies. And to analyze it, we used a fine-grained thermally aware power delivery network simulator to analyze the voltage map of the TPU and the Power 8 based dies under different cooling solutions. The power maps are calculated according to the temperature, and the maximum voltage drop in the die is computed. In general, the Fcas are able to maintain the maximal voltage drop under 5%, which is the typical constraint for high performance systems and for all the technology nodes. This is due to the lower leakage, as well as the improved power generation with high temperatures and low operation voltages. The Aurora cooling chips suffer up to 15% voltage drop with advanced process nodes, which drastically affects the performance. And finally, the fan-based ultra-scale chips suffer very high voltage drops, and that is due to the exponentially growing leakage. Overall, without the Fcas, the power delivery network requires many significant improvements in order to achieve operational deeply scaled 3D MPSoCs. And to illustrate that, we propose to quantify the additional necessary power delivery components in order to achieve the 5% voltage drop constraint in case of the Aurora cooled 3D MPSoCs. And mainly, we propose to quantify the additional TSVs and metallization layers in the back end of line dedicated to power delivery. When only TSVs are added to achieve the constraint, we show that it is necessary to add up to 11% of chip area for the Power 8 based dies and up to 10% for the TPU based die, which not only is a very high requirement, but also greatly affects routing complexity. Now, when adding both TSVs and metallization layers, we show that we need up to 5.5 percentage of area for the Power 8 based dies and up to 7% area for the TPU based die, plus 2 extra metal layers for VDD and ground voltage delivery. And knowing that each extra layer adds approximately 10% of the fabrication cost. These results further motivate the design of deeply scaled 3D MPSoC with Fcas, as they achieve the voltage drop constraints without requiring extra optimization for the power delivery network. In conclusion to this talk, we have evaluated the evolution of Fca cooling and power generation capabilities when scaling the fabrication process of 3D MPSoCs. For that, we modeled the power consumption scaling of 3D dies with different advanced technologies down to the 3 nanometer FinFET CMOS. We have demonstrated that the on-chip liquid cooling of Fcas outperforms a cooling solution of a high-performance multi-processor platform. We have also shown the sustainability of Fca voltage drop reduction capabilities due to better power generation. And finally, we hopefully motivated the usage of Fcas as an efficient solution for power management of deeply scaled 3D MPSoCs, allowing to save many power delivery network component requirements. I'd like to thank you for watching this video presentation. If you have any questions, feel free to send me an email. And of course, for further details on the work, please refer to the published paper.